Hello everyone, welcome back to Align Pattern. Today we are going to explore two important concepts in operating systems, multithreading and multiprocessing. In our previous lecture, we discussed multitasking and multiprogramming along with some multiple choice questions to test your understanding. If you haven't watched that yet, make sure to check it out. It will give you a strong foundation for today's topic. Just like before, we will not only understand the concepts but also go through a few MCQs to reinforce your learning. So, without wasting any time, let's dive into today's topic and master these concepts step by step. In operating system, multithreading and multiprocessing are two concepts used to achieve concurrent execution and improve system performance. Okay, let's break down multithreading and multiprocessing using a chess game analogy for easy understanding. Imagine you are organizing a multiple chess games in a chess tournament and you have a multiple players, multiple boards, one or more empires and one or more rooms. This is the game setup, imagine it. So in multithreading, the main concept is it has a one game and many moves at once within the same room. Okay. For example, two players playing a chess game in a room, each player is doing multiple things at the same time, like thinking about strategy, moving pieces, writing moves down in a notebook, or watching the opponent. Okay, all of these actions are part of one single game but done in a parallel threads of activity. Got it? In operating system term, we can say that one process is equal to one chess game and multiple threads is equal to different actions that players are doing. These all threads sharing the same space, or we can say that the game board, pieces or clock. Okay, this whole process is, we can call it as a multithreading in everyday example. Got it? Likewise, in multiprocessing, the main concept is to have the multiple chess games in different rooms. Now imagine you have several different chess games happening at the same time in a different rooms. Each game has its own players, its own board and pieces and its own empire. Okay, all these games are completely independent of each other. You get that, right? Okay, in operating system term, we can say that multiprocessing has each chess game is equal to a separate process and each game run in its own memory space. Somehow, if one game ends or crashes, others keep going on. This is the main difference. In short, multithreading is like a single chess game with the players doing multiple tasks simultaneously, and multiprocessing is like running many independent chess games at the same time in different rooms. Okay, I hope you got these two concepts with our everyday example. Let's now shift from the analogy to the textbook style definitions along with operating system based examples for both multithreading and multiprocessing. Okay, multithreading is a technique where a single process is split into multiple threads which are smaller independent sequence of execution. All threads share the same process memory which allows the faster communication and lower overhead compared to the processes. Okay. For example, in a web browser like Google Chrome or Firefox, each tab can be handled as a thread. While you are watching a video in one tab, another thread may be loading a web page or executing JavaScript code. Okay. Another example, as in word processor, one thread handles the text input, another checks for the spelling errors, or another auto saves the document, all in real time. Got it? Multithreading can be categorized based on how threads are managed and executed by the user application and the operating system kernel. There are four types of multithreading. User level threads that we can call as a ULT. Second one is kernel level thread, KLT. Third one is hybrid thread, which is combine of ULT and KLT. And last one is multicore or many to many threading. Okay, we will see this one by one. User level thread are created and managed in user space by a thread library. Operating system kernel is unaware of this existence of these threads. The operating system sees only one process. All thread management, that is creation, scheduling, switching of thread happens in user space only. Got it? As it doesn't require kernel involvement, thread switching is very fast. For example, green threads in Java used in early JVMs and JNU portable threads comes under this user level threading. Advantage of this kind of threading is that creation and switching is very fast. It doesn't require the operating system support and it's portable. But it has a limitation as if one thread blocks, the whole process blocks and it cannot take the advantage of multi-core CPUs for real parallelism. Kernel level threads are fully managed by the operating system kernel. Each thread is individually scheduled by the operating system and can run on separate CPU cores. In kernel level threading, operating system knows and manage each thread. Thread creation and context switching require the system calls, and threads can be scheduled independently on multiple CPUs. Remember this, okay? Example is Windows threads, Linux native threads via clone and syscall, Mac OS, POSIX threads, okay? Advantage of this kind of thread is true parallelism on multi-core processors. If one thread blocks, other can continue the execution. But it is the slower thread management due to kernel calls, and it has a higher overhead compared to user level threads. Next one is the hybrid thread, which is combination of this ULT and KLT. A hybrid threading system combines the user level and kernel level threads to offer the best of both the worlds. A user level threads library maps user threads to kernel threads. Thread creation and scheduling are done in a user space, but some threads can run in a parallel via the kernel. Okay. Then next is our multi-core, or we can say many-to-many threading. In this model, multiple user threads are mapped to multiple kernel threads. This is allow for a large number of user threads to run concurrently with the optimal kernel support. Okay. In this threading, the operating system provides a pool of kernel threads. Upon that, user level threads library schedules which user threads run on which kernel threads. Okay, this model having the high scalability and efficient on multi-core processors. Only the problem with this is that it is very much difficult to implement and manage. It still needs careful synchronization and design. If we talk about multi-threading model in operating system, there are three main types of multi-threading models, each with its own behavior, benefits and limitations. Okay. Multi-threading models define how user level threads are mapped to kernel level threads. Operating system uses these models to manage execution, scheduling and context switching. Got it? There are three primary multi-threading models which determine the efficiency, scalability and behavior of multi-threaded programs. First multi-threading model is many-to-one model. In many-to-one model, it maps many user level threads to a single kernel thread. This thread management is handled by the thread library in user space, and the kernel is unaware of the existence of these threads. In many-to-one model, if one thread makes a system call as an input-output, all threads are get blocked. As seen in diagram, all the user threads run on only one single kernel thread. Remember this, okay? Only one thread can access the kernel at a time. Many-to-one model is simpler for implementation. It does not take advantage of multiple processors. Since it's in user space, its efficient thread creation and management skill does not require the context switching between the kernel threads. In real-world example, we could take early versions of Java threads and JNU portable threads. Okay. Then our next model is one-to-one model. In the one-to-one model, each user thread is mapped to its own kernel thread. This allows true parallelism as the operating system can schedule multiple threads on a different processors. In one-to-one model, creating of thread requires the creation of corresponding kernel thread. Threads operate independently and can be executed in parallel. That is why blocking one thread does not affect others. One-to-one model provides the real concurrency on multi-core CPUs. Okay. Benefits of this kind of model is to have a better responsiveness in interactive applications. Got it? This type of real-world example is Windows OS and Linux using the POSIX P threads. But it also has limitations such as thread creation is more costly, system resources are consumed more quickly, and per process the operating system limits the total number of threads. In many-to-many model, many user threads are mapped to a smaller or equal number of kernel threads. The mapping is managed by the thread library and the kernel cooperatively. Multiple user threads are multiplexed over a smaller number of kernel threads. The system can schedule user threads to available kernel threads based on load or need. Best part of this model is it provides the flexibility and efficiency. Okay. Real world example is Solaris 9 and earlier, Windows with the Fiber API. But in many-to-many model, synchronization between thread library and operating system is much needed, and it is somewhat complex to implement. Last but not the least is two-level model, which is hybrid of one-to-one model and many-to-many model. This model is a variation of many-to-many model where some user threads are bound directly to specific kernel threads while others are multiplex over the kernel threads. In the two-level model, a subset of user threads can have a one-to-one mapping with the kernel threads and the rest of the threads behave in a many-to-many manner. Example of this type of model is Solaris 8 and onwards. The basic advantage of two-level model is that of useful behavior of application with both computer bound and input-output bound threads. It combines the flexibility of many-to-many and the performance of one-to-one. Okay, so this is the multi-threading in operating systems, including all the major models and their respective types. I hope the explanation is clear and that you were able to understand everything covered. Now let's explore the concept of multiprocessing in operating system. In this topic, we will understand what multiprocessing means, how it functions within an operating system, its types, advantages, and how it differs from other processing techniques such as multithreading, or we can say simply multitasking. Okay, it involves the use of two or more processors that share the same physical memory and communicate with each other under the control of a single operating system. Each processor can work on different tasks or on different parts of the same task, thereby improving the system's overall speed, efficiency, and reliability. In multiprocessing system, multiple central processing units are integrated into a single computer system. These CPUs are tightly coupled, meaning that they are connected and work closely together through a shared memory and communication infrastructure. In multiprocessing, all the processors are located in a close physical proximity. They work in a coordination under a single operating system, and communication is very fast due to shared memory and the buses. Okay, input-output devices such as keyboard, disk, network are shared by all the CPUs. A single main memory is accessible by all the processors. This shared memory model ensures the consistency and easier data exchange. Operating system is responsible for managing process scheduling, resource allocation, and interprocessor communication. It manages the process scheduling, that is decided which CPU runs which task. Handles the resource allocation, memory, input, output, and CPU time, and ensures the interprocessor communication and synchronization using semaphores, message passing, or shared data structure. Okay. Depending on the architecture and how tasks are assigned, multiprocessing systems are classified into several types: symmetric multiprocessing, which we call SMP, asymmetric multiprocessing, ASMP, massively parallel processing, MPP, and tightly coupled versus loosely coupled multiprocessing. Okay, first one is the symmetric multiprocessing. Symmetric multiprocessing, which we call SMP, is a system where each processor runs on identical copy of the operating system and has equal access to all hardware resources. Okay, in simple term, we can say that it shares the memory and input output and have equal priority to all the CPUs. Got it? Here, operating system uses a single queue of processor, or we can say threads. Okay, the advantage of this kind of model is high throughput and performance, easy to program, cost effective for moderate workload, and limitation as contention in share memory, limited scalability. The real life example of this kind of processing is most modern desktop computers and servers and Intel and AMD multi-core processors. Got it? In asymmetric multiprocessing, each processor is assigned a specific task. A master CPU controls the system and assigns work to the other, which is called it as a slave CPUs. The master processor takes all the control of system operations, including managing the ready queue and assigning tasks to the slave processor. Slave processors do not make independent scheduling decision. Instead, they execute the processor as directed by the master. The master processor maintains the scheduling logic and distributes ready-to-run processors to the slave CPUs. This whole centralized control approach simplifies the design and coordination but may limit the parallel efficiency compared to symmetric multiprocessing. Real-life example is early multiprocessor system and some embedded system and firmware architecture. Next is massively parallel processing. In this system, it consists of many processors, 100 or 1000, each with its own memory and operating system connected via high-speed interconnect. A real-life example is supercomputer like Cray, IBM, Blue Gene, and scientific computing clusters. Advantage is that it has excellent scalability, extremely high computing power, and limitation is that complex to program and manage and high cost. Next, last one is the tightly coupled versus loosely coupled multiprocessing. Tightly coupled system, also known as a shared memory multiprocessing system, which consists of multiple processors that share a common main memory, clock, and input-output devices. All processors operate under a single operating system and communicate via the shared memory. Whereas loosely coupled system, also known as the distributed system or the cluster system, consists of multiple autonomous processors, each with its own local memory and clock. These systems are connected via communication network and typically run independent operating system, collaborating only when needed. Okay, tightly coupled systems are best for the system requiring the high-speed communication and share resources like personal computers, servers, and real-time system. Whereas loosely coupled systems are ideal for large-scale distributed computing, where fault tolerance and scalability are crucial, such as cloud infrastructure and data center. The choice between the two depends on application requirement, performance speed, cost constraint, and system complexity. Got it? I hope this detailed explanation helped you clearly understand the concept of multithreading and multiprocessing. In the next lecture, we will go through some of the top MCQs based on these topics. Until then, keep studying and stay focused.